3. Atlas begins as a dim, easily ignored mark on an electronic sky. One more flicker among millions logged by automated surveys that sweep the darkness in regular patterns. Software compares new images with old, searching for motion, and flags a faint point that shifts against the fixed lattice of distant galaxies in a way that suggests an orbit not bound to the sun. Ground-based telescopes pick it up and trace its position night after night, turning that tiny displacement into a path that arches in from interstellar space. Early reports describe a likely cometary body following a hyperbolic trajectory. Interesting, but no longer unprecedented in a solar system that has already hosted more than one traveler from beyond. On the first stacked images, the object appears as a small, soft glow, slightly elongated in the direction opposite the sun. It looks like a standard coma, the hazy cloud of gas and dust that forms when sunlight warms a frozen surface and lifts material into space.
The solid nucleus remains hidden at the heart of this glow, wrapped in a luminous shell that smooths away fine details.
To astronomers accustomed to working with such images, 3I Atlas appears at first to be routine. This impression matters because it makes what follows harder to dismiss as wishful thinking. Hubble Space Telescope time is scarce and carefully guarded, awarded only when a target promises to answer questions that cannot be reached in any other way. For a while, 3I Atlas sits near the bottom of competing lists, dim and distant and outwardly ordinary. Proposals nevertheless argue that an interstellar visitor deserves space-based attention simply because it is interstellar, and that only a stable, atmosphere-free platform can resolve structures near the nucleus while the object is still far from the inner planets. Review panels eventually agree to dedicate a modest sequence of observations.
During the closing weeks of the year, Hubble turns toward a patch of sky that would otherwise be empty, tracking the visitor as it creeps against the starfield. Over several sessions, it captures a series of exposures in different filters, each one a narrow window in which the object appears as a blurred knot of light, with a broad, diffuse tail. First looks at the raw frames reveal nothing startling. The coma appears smooth, the tail wide and unstructured, the brightness increasing at a rate broadly compatible with standard models of how a comet responds to growing solar heat. For a time, 3I Atlas remains an abstraction, a catalog of positions and magnitudes, a small smear on screens in control rooms and offices. Yet, beneath the surface of this familiarity, small tensions begin to form. When teams plot the brightening against distance, the curve does not fall neatly where theory would place it for a simple, icy nucleus of plausible size. The coma shows subtle asymmetries from one side to the other, as if certain regions on the unseen surface are more active than others, and faint hints of narrow enhancements appear when the images are stretched to extremes. Taken alone, each of these features could be dismissed as noise, artifacts of processing, or consequences of background contamination. Taken together, they leave a slight residue of unease. It feels as if the object is trying to hint at a more intricate internal pattern, while still keeping its true shape hidden. 3. iAtlas settles into an ambiguous status within the community. Official circulars describe it with restrained language and conventional terminology. Informal conversations circle around it more restlessly, raising possibilities of unusual spin states, patchy surface composition, or complex topography on the nucleus. The central question that keeps returning is simple. What would the inner core look like if the coma could be peeled away? The data sitting in archives hold a potential answer, but it is still buried under the blur. Transforming that blur into structure will require more than standard reductions. It will demand techniques designed to emphasize subtle gradients and rotating patterns, tools that can make moving features stand out against the soft shell of dust. For now, the visitor glides onward along its calculated path, indifferent to the growing curiosity it inspires. In the cold space between the planets, sunlight continues to warm its surface, feeding the diffuse halo that hides whatever geometry waits at the center. The human view is still of a smudge that behaves almost like all the others. Almost, but not quite. That small difference is enough to keep attention fixed on this faint intruder from the dark, and to set in motion the deeper analysis that will soon change a routine comet into the seed of a larger mystery. In the quiet after the first round of observations, attention shifts from gathering more photons to squeezing more meaning from those already captured. The blurred knots of light recorded by Hubble carry information that the eye cannot see, gradients of brightness and subtle streaks smoothed together by the haze of the coma.
To reveal hidden structure, astronomers turn to tools that enhance features sharing the rotation and motion of the underlying object. Among these is the Larsen-Sekanina rotation gradient filter, a digital technique that compares each point in the image with neighbors along a circular path and amplifies any consistent difference. Applied to ordinary comets, such a filter often transforms a smooth halo into a richer scene of fans, spirals, and irregular jets tied to active regions on the nucleus. When the same process is applied to the Hubble images of 3I Atlas, the familiar smudge begins to dissolve.
The wide, soft glow that once filled the frame is suppressed, leaving behind a leaner pattern. The coma seems to fall away like mist. What remains is not a random spray, but 3 narrow, bright lines extending outward from the central core, each one like a needle drawn in light. They appear remarkably straight, and, more importantly, they appear remarkably balanced. The 3 jets diverge from the nucleus at angles that, when measured, cluster around equal separations. Within the uncertainties of the method, each jet stands roughly 1/3 of a full circle from the next. The configuration resembles an equilateral triangle, traced not in solid matter, but in directed outflow. An arrangement more reminiscent of engineered thrusters than of the uneven vents usually seen on natural comets. This impression could be an illusion, so the teams check. They vary the parameters of the filter, rotate the frames, test individual exposures as well as stacks, and apply alternative methods that should highlight any genuine feature while washing out noise. Each time, the same basic pattern returns. 3 jets, thin and distinct. 3 directions, spaced with quiet regularity. The possibility of bias hangs over the work, so independent groups repeat the analysis without sharing intermediate steps. Their results converge on the same geometry. The next question is whether such geometry can arise by chance from natural processes. Comet nuclei are not smooth spheres. They are irregular bodies with pits, cliffs, and fractures, relics of repeated encounters with deep space and earlier passes near stars. Gas escaping from such surfaces tends to be channeled through weak zones, so it is not surprising to see jets at all. What is surprising is their arrangement. If vents open wherever conditions permit, their directions should be scattered. Some may be roughly aligned, others may lie at random angles. To find 3 that are not only present, but placed so close to equal angular spacing requires an unlikely combination of shapes and stresses. Using simple models that scatter vent locations over a rotating nucleus, researchers estimate how often such a balanced pattern should appear if nature alone sets the rules. The numbers suggest that the chance of this precise symmetry arising from random vent placement is roughly 0.2%, about 1 in 500 trials. That estimate is not a proof, but it is a warning that coincidence is being asked to carry a heavy load. Most comet nuclei visited by spacecraft look like misshapen boulders, rubble piles whose active plumes erupt from scattered sites with little regard for geometric order. None has yet shown 3 persistent jets arranged in such clean angular spacing. The filtered images of 3I Atlas therefore occupy an uncomfortable space between familiarity and strangeness. They still show a coma and tail, still display the broad behaviors expected of a comet driven by sunlight. Yet at their center sits an arrangement that looks unnervingly tidy. It evokes the threefold layout that engineers favor when they wish to stabilize a spinning craft, placing thrusters at equal angles so that their combined forces keep the body from wobbling. The comparison does not prove design, but it makes the pattern hard to ignore. As the processed frames circulate, reactions split. Some see an extreme but still possible outcome of natural evolution, perhaps the result of a specific kind of contact binary with vents on each major lobe. Others see the first hint that the interstellar visitor is not simply a fragment of frozen debris, but a structured architecture whose internal architecture shapes its activity. With each iteration of the analysis, the smudge that once seemed unremarkable recedes further into the past. In its place stands a sharpened figure of 3 balanced jets. A quiet but insistent sign that 3I Atlas may be telling its story in the language of geometry. The symmetry of 3I Atlas settles over the data like a quiet challenge, asking the same question from many angles. How comfortable is nature with perfection on a grand scale? On small scales, symmetry is almost expected. A snowflake grows into 6-fold patterns as water molecules stack themselves according to the shape of their bonds. A crystal forms repeating lattices as atoms settle into regular positions.
Many living forms echo bilateral or radial balance because it emerges from simple rules in growing tissue. In these domains, symmetry flows directly from the physics of repeated units and self-similar growth. On the scale of a mountain-sized fragment of interstellar rock and ice, however, order usually loses its grip. Collisions, fractures, and uneven heating distort whatever pure forms might once have existed. Comet nuclei, photographed up close, resemble eroded cliffs and boulders, their vents clustered in chaotic patches that trace the history of impacts and stresses.
Against this backdrop, three jets, spaced almost exactly one-third of a full circle apart, stand out like the clean lines of a compass drawing etched across a landscape of rubble. When researchers speak of a probability of about 0.2% for such a pattern to arise by chance, they are not claiming certainty, but they are quantifying unease. That number emerges from simple experiments in simulation. Virtual comet surfaces, irregular and multifaceted, are seeded with active vents at random locations. The model nucleus spins, and synthetic images are generated to mimic the way gas and dust would stream outward. Repeating this process many hundreds or thousands of times generates a catalog of patterns, most messy, some partially ordered. Only a small fraction display three dominant jets, and only a smaller fraction place those jets at nearly equal angular separations. Counting these rare alignments yields a rough estimate. Perhaps one case in 500 mimics the neat equilateral structure seen in the Hubble filtered images. In the language of statistics, that rarity corresponds to a modest but noticeable deviation from what would be expected if there were no underlying tendency toward order. Scientists sometimes describe such deviations in terms of a confidence level, expressing how strongly the data argue against pure randomness. The exact threshold for calling a discovery convincing varies from field to field. But the deeper issue here is not a rigid line between possible and impossible. It is the growing tension between what experience says a natural comet should look like and what 3I Atlas actually shows. Nature can certainly surprise with structured forms on large scales. Spiral galaxies trace glamour arms. Planetary rings arrange themselves into bands and gaps, and even some asteroids reveal bilobed shapes that hint at complex histories. Yet these structures usually come with clear physical stories. Rotating disks fragment under gravity. Resonances with nearby bodies carve gaps. Slow mergers between rubble piles produce dumbbell figures. In the case of 3I Atlas, the known processes driving comet jets do not naturally pick out three directions separated so neatly in angle. The gas flows where the surface is weak and where heat penetrates most deeply, often along fractures or through pits formed by earlier outbursts. The odds that three such weak zones would lie at just the right longitudes to form an almost perfect triangle, and that each would be active with similar intensity at the time of observation, stretch the idea of coincidence thin. The mind reaches instinctively for analogies with engineered systems. When humans design a spinning spacecraft, placing thrusters or reaction wheels at threefold symmetry is a common way to ensure stable control. Three equally spaced forces can cancel out wobble and maintain orientation with minimal effort. The filtered images of 3I Atlas, with their three needle-thin plumes, resemble such a stabilizing scheme more than they resemble the chaotic sprays seen on many comets. This resemblance does not prove intent, but it makes the case for pure randomness feel less satisfying. Some researchers respond by sharpening natural explanations. They propose that the nucleus may be a contact binary or even a triple structure, with major lobes arranged in a way that naturally produces three preferred directions for outgassing. In this picture, the balanced jets are not the result of deliberate placement, but of slow gravitational settling between components over millions of years. Others suggest that the spin axis and illumination geometry might conspire to bring only three vents into view at the moment of observation, masking a more irregular network of sources. Each of these models softens the apparent improbability, but often at the cost of adding layers of assumption that cannot yet be tested directly. The probability estimate of 1 in 500 sits in the middle of this debate like a quiet figure on a page. It is low enough to raise eyebrows, but not low enough to close the argument. It leaves room for cautious statements and guarded counterarguments, for those inclined toward conservative interpretations and those willing to entertain more radical possibilities. As the discussion unfolds, the symmetry of 3I Atlas begins to feel less like a trivial curiosity and more like a potential clue. If geometry is the only reliable language that can bridge immense distances and unknown cultures, then a pattern that strongly resembles a threefold stabilization scheme acquires a faint flavor of communication. At the same time, if nature is capable of carving such a pattern in ice and rock without any guiding hand, then the universe is stranger and more inventive than current models fully capture. In either case, the three jets of 3I Atlas stand as a quiet statement written in the most economical form: 3 lines, 3 angles, a triangle inscribed in outflowing gas, waiting for an interpretation that does not yet exist. As soon as the sharpened images of 3I Atlas reveal their threefold pattern, the instinct of the scientific community is to search for the most conservative path back toward familiarity. The first and strongest candidate is the contact binary, a configuration in which two separate bodies have drifted together and fused gently into a single irregular mass. Such shapes are common in small solar system objects. A slow collision between icy fragments can produce a nucleus with distinct lobes joined by narrow necks, and the resulting topography can funnel gas into preferred directions when sunlight warms particular regions. If 3I Atlas is such a fused body, then perhaps each of its major lobes hosts a dominant vent, and the geometry of the merger has placed these vents at longitudes that, when projected onto the sky, mimic an equilateral triangle. The idea is appealing because it does not require any new physics. Tidal encounters, collisions, and gradual spin-up under sunlight can all reshape a comet over time, aligning surface cracks and weak zones in complex ways. A contact binary can also explain asymmetries in the coma brightness and subtle changes in the light curve as the nucleus rotates, features that already hint at an uneven shape. Under this model, the three jets are the visible expression of deeper structural quirks inherited from a long and chaotic history in another stellar system. Yet, when this explanation is pushed against the details of the data, it begins to show strain. A contact binary can readily produce multiple active regions, but the odds that exactly 3 dominant vents would sit at nearly equal angular separations remain low, unless the merger happened in a very specific orientation. Modelers can construct artificial binaries whose lobes are arranged so that their main weak zones line up in the required pattern, but often this involves choices that are guided by the desired outcome rather than by independent evidence. The result is a narrative that fits the observations because it has been tuned to do so, rather than a configuration that falls naturally out of well-understood dynamics. Another line of explanation invokes the rotation of the nucleus itself. If 3I Atlas spins in such a way that certain regions receive repeatable, focused heating from the sun, then those regions may develop active vents while others remain dormant. Over many rotations, small differences in temperature and stress can grow, carving preferred channels for gas to escape. In this view, the three jets are not anchored to permanent surface features so much as they are sculpted by the interplay between spin axis, orbit, and illumination. A slight tilt of the axis, combined with an uneven distribution of volatile material within the interior, might pick out 3 long-lived outflow directions that appear almost perfectly balanced for a time. This mechanism leans on the known tendency of sunlight to torque small bodies and to drive complex feedback between rotation and outgassing. It can, in principle, generate structures that appear organized without any guiding intelligence. Again, though, the match to the specific case of 3I Atlas is not entirely comfortable. To maintain 3 narrow, stable jets arranged so neatly in angle over the span of the Hubble observations, the rotation state must occupy a tight range of possibilities. Too slow, and the heating pattern would smear across the surface, activating broader regions rather than 3 precise vents. Too fast, and centrifugal effects would alter gas flows in ways that tend to blur out symmetry. The axis must be aligned so that each active zone receives similar energy and presents a similar projected angle to the line of sight. Otherwise, one jet would appear fainter or more diffuse than the others. The need for such exact tuning makes this rotational scenario feel less like a simple, robust explanation and more like a stack of balanced conditions. There are additional hypotheses. Some suggest that fractures propagating through the nucleus may have followed stress lines set during the object's formation in its home system, creating 3 dominant fault planes spaced by roughly equal angles. Others imagine that earlier close passes by other stars or massive planets could have torqued the core into a shape that naturally favors threefold outgassing. Each explanation uses familiar ingredients: gravity, heat, stress, ice, dust. None requires exotic physics or deliberate intervention. Yet each must inherit or impose a geometry that just happens to yield the triad seen by Hubble. The more possibilities are explored, the more the situation begins to resemble a puzzle in which every natural piece can be made to fit only by leaning on special initial conditions. There is also the question of persistence. The filtered images capture 3I Atlas at specific times, but the visitor is in constant motion, rotating and advancing along its hyperbolic path. If the three jets are tied to surface structures, their appearance should change as different facets turn toward or away from the sun. If they are artifacts of processing or chance alignments of faint knots in the coma, then subsequent observations with different geometry should wash them away. Instead, follow-up analyses hint that the threefold pattern, while varying in brightness and sharpness, remains broadly recognizable across multiple sessions. This persistence adds another weight to the side of deliberate structure, whether natural or artificial. In private discussions, some researchers admit that the contact binary and rotation-based models feel fragile, useful as working hypotheses, but not yet satisfying as complete stories. They keep these reservations to themselves in formal notes, where caution governs language and where extraordinary claims are carefully avoided. Outwardly, the consensus still leans toward natural explanations, because history has shown that strange data often melt into familiarity once more information is gathered. Inwardly, a small but growing minority begins to wonder whether the insistence on forcing 3I Atlas into familiar shapes might be obscuring a more radical possibility. If every conventional model must be finely tuned to reproduce the same simple pattern, perhaps the pattern itself deserves to be taken more seriously as a primary clue, rather than as an anomaly to be explained away. The contact binary remains on the table, but beside it now sits a quieter suggestion: that 3I Atlas may be a structure whose symmetry is not a byproduct of chance, but a defining feature. As debate circles around natural explanations, another line of thought begins to trace a more speculative contour through the data, one that treats the symmetry of 3I Atlas not as an inconvenient coincidence, but as a candidate signature of technology. The concept of a technological signature, sometimes shortened in expert discussions to a technosignature, rests on the idea that advanced engineering leaves patterns in light and motion that differ subtly but measurably from those produced by untended nature. In this framework, the three needle-fin jets, arranged with near-perfect angular balance, become more than curious plumes of gas. They start to resemble the controlled outputs of a system designed to maintain stability, much like the thrusters on a spacecraft that keep its spin aligned. The comparison gains weight when placed beside earlier interstellar visitors. The first, an elongated object that swept through the inner solar system several years before, showed a small but persistent deviation from the path predicted by gravity alone. Its brightness varied in a way that suggested a thin, flattened shape, yet it displayed no obvious coma, despite passing close enough to the sun for many ices to sublimate. Models invoked unfamiliar kinds of outgassing or unusual structural properties, but some researchers quietly proposed that it might be a fragment of engineered material, perhaps a light sail, or a shard of a larger construct built to ride radiation pressure. A second interstellar visitor, more clearly cometary, behaved in a way that fit more comfortably within existing understanding, its extended tail and rich gas emissions offering fewer reasons to reach for technology. 3I Atlas arrives in the shadow of these precedents, carrying aspects of both. Like the second visitor, it possesses a substantial coma and a long, chaotic tail, a clear sign that sunlight is lifting matter from its surface. Like the first, it exhibits anomalies that resist easy classification, most notably the balanced trio of jets and subtle hints of non-gravitational effects in its motion that remain within the margins of error, but lean in a suggestive direction. In considering a technological interpretation, astronomers do not immediately leap to images of spacecraft in the familiar sense. An engineered object designed by a civilization separated by vast distances and unknown biology might bear little resemblance to human hardware. Instead, the analysis focuses on functions that would be universal. Any device that must maintain orientation while drifting through space will face constraints imposed by physics. If it spins, it must manage angular momentum. If it adjusts its trajectory without relying solely on gravitational assists, it must direct thrust. In this light, three equally spaced jets become a simple, robust solution. They offer redundancy, balance, and fine control, allowing small adjustments without inducing unwanted wobble. The fact that 3I Atlas appears to apply its outgassing in precisely such a pattern makes the technological lens difficult to dismiss outright. At the same time, the history of science warns that patterns can mislead. Humans are adept at finding shapes and order even where none exist, a tendency that can turn random noise into imagined signals.
To guard against this, proponents of the technosignature view anchor their arguments in measurable quantities. They point to the estimated probability of the jet arrangement arising by chance, to the persistence of the pattern across multiple observations, and to the resemblance between the inferred force layout and standard schemes used in attitude control engineering. They also note that the interstellar origin of the object removes certain local formation scenarios, since its home environment may have been quite different from the solar system's own protoplanetary disk. Under these conditions, 3I Atlas becomes an experiment framed by a simple question. If a distant civilization wished to send durable hardware between stars while keeping its design as efficient and general as possible, might it choose something like this? Opponents of the technological interpretation emphasize the dangers of extraordinary conclusions drawn from limited data. They stress that cometary physics remains an active field, with many processes still only partially understood. Complex fracturing, layered volatile deposits, and long-term evolution under variable stellar environments could conceivably produce structured outgassing that mimics deliberate control. They remind colleagues that earlier hints of artificiality in astronomical phenomena, from peculiar star-dimming patterns to unusual radio bursts, have often faded as more mundane explanations emerged. The tension between these perspectives shapes the discourse around 3I Atlas. Neither side can claim decisive evidence. There is no obvious radio emission, no regular beacon-like modulation, no sharp spectral line that screams machinery. What there is instead is geometry, motion, and probability. The threefold symmetry does not act alone. It is accompanied by the broader context of an interstellar trajectory, a finely balanced coma structure, and a set of behaviors that straddle the line between known comet families and something other. In this context, technology becomes one hypothesis among several, constrained not by narrative preference, but by the same demand placed on any natural model. It must account for the data without relying too heavily on special pleading. The idea that 3I Atlas could be a piece of purposeful hardware, perhaps long dead, perhaps still functioning in some reduced capacity, carries with it a quiet sense of contact without conversation. If this object is engineered, then its creators are unlikely to be watching its passage through a distant planetary system, and the system itself may not be its intended destination. It could be debris, a probe, a part of a larger fleet, or something else entirely beyond human categories. For now, the technological signature remains a whisper, a line of reasoning that does not yet rise to declaration, but that sits in the background of every new measurement. As more data accumulate, the balance between natural and artificial explanations may shift. The three jets continue to shine in processed frames, a pattern written in gas and dust that invites engineers and theorists alike to imagine what sort of device would look like this from afar, and what purpose such a device might serve as it drifts through the quiet between stars. As the threefold core of 3I Atlas comes into sharper focus, the contrast with its surroundings grows more dramatic. In wide-field images from Hubble and from large telescopes on the ground, the visitor appears wrapped in a vast shroud of dust and gas, a tail extending perhaps 100,000 kilometers or more along the direction opposite the Sun. On these scales, the tail overwhelms everything else. It fills the frame as a pale plume, rippled and frayed, bending under solar radiation and the charged wind that streams outward from the star. Filaments curl and shear, knots of brightness form and disperse, faint waves sweep along its length. It is a shifting, restless structure, a record of countless grains and molecules pushed and pulled by forces that never arrange themselves in quite the same way twice. This outer chaos is familiar. Comet tails normally behave like this, as the integrated outcome of many small events switching on and off, each contributing its own uneven share of material. Usually, the disorder of the tail echoes the irregularity of the object at its heart. A rough nucleus with patchy active regions sends out broad, overlapping fans of gas and dust, and observers can often trace major features in the coma to corresponding zones on the surface. With 3I Atlas, that link seems strangely weakened. The tail behaves like that of a vigorous comet, even showing hints of an anti-tail when perspective lines up dust along the path of motion. Yet, near the core, the filtered images reveal a discipline that the halo does not share. Within a region only a few tens of thousands of kilometers across, rotation gradient processing isolates three thin jets that cut through the diffuse glow like straight beams. They seem to spring from near the hidden nucleus, remain collimated over surprising distances, and feed the larger outflow without immediately dissolving into it. In visual terms, it is as though a compact engine with three steady exhausts is embedded inside a storm that it both drives and endures. The difference in scale between ordered inner jets and turbulent outer tail recalls layered systems elsewhere in astrophysics. Planetary atmospheres can carry narrow jet streams within much broader belts of cloud. Magnetic fields channel charged particles along invisible lines, producing slender auroral arcs against a more diffuse background. In such settings, simple underlying structures impose order on larger, messier domains. If something similar is at work in 3I Atlas, then the three jets may act as the organizing framework of the entire coma, primary channels through which momentum and material are injected before being scattered into the wide tail.
The apparent instability of the far plume would then be a secondary effect, while the persistent geometry close to the core would mark the true character of the object. Observations across the coma lend cautious support to this layered picture. Brightness profiles show that certain directions from the nucleus carry disproportionate amounts of light and dust, aligning with the jet axes identified in processed frames. Measurements of polarization, which track how grains scatter sunlight, sometimes peak along the same directions, hinting at coherent flows or aligned particles emerging from specific sources. Spectra reveal common volatile species, such as water and carbon-bearing molecules, but small shifts in their relative strengths near the jet directions suggest that the material feeding those outflows may come from interior reservoirs with slightly different histories. None of these signatures alone is striking enough to demand a new category of object, yet together they sketch a scene in which 3I Atlas operates like a layered engine. Interior ices vent through three dominant chimneys. Their outflows carve narrow channels through the inner coma, and only beyond that region does the gas and dust fan out into the sprawling, ever-changing tail that the sun sculpts from the released material. A configuration of this kind could arise without any guiding intelligence. An interstellar body assembled in another planetary system might naturally accumulate different materials at different depths, later reshaped by slow heating and stress into a structure with three main weaknesses. Once opened, such channels would govern the behavior of the coma for as long as sufficient volatile material remains, preserving the contrast between inner order and outer chaos over many weeks or months. At the same time, the efficiency of this layout invites a more speculative reading. Engineers who wish to move mass and control spin with minimal waste tend to prefer a small number of well-placed outlets over many uncontrolled leaks. Three balanced jets can stabilize a rotating body while shedding energy in a predictable way. If 3I Atlas is a relic of purposeful design, then its appearance would naturally separate into an inner zone where geometry dominates, and an outer zone where that geometry interacts with whatever environment it encounters. Under that view, the chaotic tail is almost incidental, a veil that varies from system to system, while the quiet triangle close to the core is the constant signature. That signature is what the filters keep finding. Three lines, steady in their angular spacing, even as brightness and background change. Whether carved by slow natural evolution or by deliberate engineering, the tension between serene inner symmetry and wild outer motion gives the object an oddly architectural character. It resembles a framework glimpsed through moving fog, the same beams appearing again and again while clouds shift around them. Each new observation reinforces this dual image. Deeper exposures reveal fresh ripples far down the tail, while repeated processing near the nucleus continues to recover the same threefold pattern. The message, if there is one, remains unclear, but the structure that carries it keeps repeating. 3I Atlas is not simply a lump of ice dissolving evenly into space. It is a system in which the core insists on balance, embedded in a halo that refuses to stay still. While 3I Atlas continues to shed gas and dust, its path through the solar system bends toward a larger stage. Calculations of its orbit reveal a hyperbolic track that threads the outer planetary region and passes close by the immense gravity well of Jupiter. The date marked on mission planning charts is mid-March of 2026, when the interstellar visitor reaches its point of closest approach to the gas giant. From the perspective of celestial mechanics, this encounter is more than a simple waypoint. It is a test, an experiment set up by nature in which an object with delicate internal structure brushes past a world whose gravitational pull has reshaped comets and asteroids many times before. Jupiter has long acted as a kind of gatekeeper for the inner solar system. Its mass, more than twice that of all the other planets combined, gives it a gravitational field strong enough to deflect, capture, or tear apart small bodies that wander too near. Streams of comets have been caught into looping orbits, only to be ejected again into interstellar space after close interactions. Others have been shredded into chains of fragments when tidal forces exceeded the cohesion of their icy cores. The most famous example in recent history is a comet that arrived as a single object and was pulled apart into more than 20 pieces, each of which later plunged into the Jovian atmosphere in a sequence of impacts that left bruised scars across the cloud tops. Those events demonstrated in vivid fashion how Jupiter can act both as protector and as destroyer, intercepting potential impactors that might otherwise reach the inner worlds, while at the same time erasing the integrity of fragile visitors. Against this backdrop, the prospect of 3I Atlas sweeping past the same planet acquires particular significance.
If its nucleus is a loosely bound rebel pile, perhaps a contact binary, only barely held together by weak gravity and cohesive forces, then the differential pull across its length as it passes near Jupiter could overwhelm that grip. Tidal stretching might open new fractures, widen existing cracks, or even separate major lobes into distinct pieces. Observers would see the narrow triad of jets distort, multiply, or collapse into a more chaotic spray as the underlying structure fails. The tail could break into multiple strands, each tracing the path of a fragment, now following its own slightly different trajectory. Such a disruption would not only reveal the interior weakness of the object, but would also offer clues about its density and composition, as the degree of deformation would depend on how mass is distributed within. On the other hand, if 3I Atlas is more solid than its cometary envelope suggests, or if its internal architecture is somehow reinforced, it may pass through Jupiter's sphere of influence with its geometry largely intact. In that case, the threefold symmetry of the jets would provide an anchor against which small deviations in motion could be measured. As the object feels the combined influence of Jupiter's pull, solar radiation, and its own outgassing, any departure from the purely gravitational path can be examined with exceptional sensitivity. This is because Jupiter's mass fixes the expected deflection to high precision. A tiny difference between prediction and reality, especially if it carries the imprint of directed thrust rather than simple radiative pressure, would stand out more clearly against the strong background of the planet's influence. Mission planners and observers treat this passage as an opportunity comparable to a laboratory experiment. Spacecraft already in the Jovian system, particularly those in polar orbits around the planet, can be tasked to pivot their instruments toward the incoming visitor when geometry allows. They will not approach as closely as dedicated rendezvous missions once did with comets in the inner solar system, but they can still gather data that complement the view from Earth. Images, even if no sharper than those from Hubble, can reveal changes in the coma and jets triggered by the intense tidal field. Spectrometers can sample how gas production rates respond to the enhanced stress and to subtle shifts in sunlight at that distance. At the same time, a network of ground-based telescopes and other space observatories will track the object's position with exquisite care, refining its orbit before, during, and after the encounter. By comparing the inbound and outbound trajectories, dynamicists hope to detect any non-gravitational acceleration, however slight. Comets often experience such kicks when one side becomes more active than the other, effectively acting as a natural thruster. In most cases, the pattern of these forces is complex and irregular. For 3I Atlas, the presence of three balanced jets offers the possibility that any net push will follow a more coherent pattern. If the jets respond to Jupiter's passage by adjusting their intensity in a way that preserves spin and orientation, the resulting subtle course changes might carry a signature of control rather than of random venting. The physical distance at closest approach is great enough that a direct collision is avoided, but close enough that Jupiter's gravity will shape the future of the object decisively. It may leave the solar system on a slightly altered path, its hyperbolic arc stretched or compressed by the interaction. It may be captured into a long, looping orbit before eventually slipping away again into interstellar space, carrying with it the imprint of this brief visit. Or it may be broken into pieces that trace divergent routes, some lost into the depths of the Jovian system, others flung back toward the void. Each scenario writes a different ending for the current apparition, and each offers a different window into what 3I Atlas truly is. As the date of the encounter approaches, the sense of anticipation grows. Observers refine their models, simulate countless versions of the flyby under varying assumptions about mass, structure, and spin, and prepare their instruments for rapid, responsive work. Underneath the technical planning lies a more quiet expectation. Whatever happens near Jupiter will not only test the physical resilience of this interstellar visitor, it will also test the ideas that have been built around it. A disruption would favor explanations grounded in fragile natural architectures. A smooth, controlled passage with persistent, balanced jets and measurable non-gravitational drift would keep the possibility of a designed object alive.
In either case, the gas giant will act as an unwitting interrogator, pulling at the seams of a mystery that has so far been inferred only from filtered light. As the projected date of closest approach draws near, the watch on 3I Atlas tightens into a coordinated vigil that spans instruments, wavelengths, and worlds. On and around Jupiter, the Juno spacecraft continues its looping polar orbits, diving close to the cloud tops and then arcing far out over the poles. Mission planners study its schedule and geometry, looking for windows when the spacecraft can safely turn its cameras and sensors away from the planet to catch brief glimpses of the interstellar visitor against the starfield. Juno is not a dedicated comet chaser, but its sensitive instruments can still measure changes in the local environment, monitor charged particles, and capture images that, when carefully processed, reveal the shape and brightness of 3I Atlas from a vantage point impossible to reproduce from Earth. Even a handful of frames showing the coma and jets from within the Jovian system will add an extra dimension to the data, allowing researchers to compare how the object appears from two very different perspectives at nearly the same time. Around Earth, a network of observatories prepares for an intensive campaign. Large telescopes equipped with adaptive optics systems stand ready to squeeze as much resolution as possible from the visitor's image, while smaller telescopes contribute continuous monitoring that can track variations in brightness and tail structure. Space-based assets, including Hubble and other orbiting observatories, are cued to take advantage of their freedom from atmospheric blurring. Requests for observation time emphasize not only the scientific novelty of an interstellar comet threading past a giant planet, but also the specific opportunity to test whether the mysterious threefold symmetry of the jets can survive under severe tidal stress. Astrometric teams refine their techniques to measure the object's position against background stars with extraordinary precision, aiming to detect shifts amounting to only a tiny fraction of an arcsecond. Photometric specialists design campaigns to record the brightness of the coma and jets in multiple filters, hoping to tease out subtle changes in color and composition that might betray new vents opening, old ones shutting down, or deeper layers of material being exposed. Spectroscopists prepare to dissect the light into its component wavelengths, searching for familiar lines of water, carbon monoxide, and other volatiles, as well as for any unexpected features that might hint at exotic chemistry or processed materials. In parallel, theorists and dynamicists set up models to compare with the observations as they arrive. They produce families of simulated trajectories for 3I Atlas under different assumptions about its mass, internal structure, and outgassing pattern. In one set of scenarios, the jets are treated as purely natural, their strengths fluctuating randomly within ranges calibrated to similar comets. In another, the jets are given more disciplined behavior, adjusting in intensity in ways that maintain spin and orientation. These artificial constructs are not claims about reality so much as thought experiments, designed to show what the sky path of the object would look like under various regimes of control or chaos. As data accumulate, these predicted curves will be overlaid on the actual measured positions. If the object's motion remains entirely consistent with gravity plus modest, irregular outgassing, the cloud of possible models will collapse toward the natural end of the spectrum. If instead, the trajectory shows gentle but coherent deviations, always nudged in ways that preserve orientation or avoid particular gravitational configurations, the technological scenarios will gain weight. Within this broader effort, the three jets themselves remain the focal point. Observers plan sequences of images timed to sample different phases of the object's rotation, allowing them to see how the jets sweep through space. Changes in their relative brightness can trace which vents are active at any given moment, while changes in their apparent direction can constrain the spin axis. During the days around the Jupiter passage, special attention will be given to whether the angular spacing of the jets remains as close to 1/3 of a full circle as earlier measurements suggest. If tidal forces distort the nucleus, the jets may wobble, split, or drift out of their precise arrangement. If, instead, they hold their spacing with stubborn resilience, even as the tail whips and stretches under the giant planet's influence, then the impression of a stabilizing geometry will harden. Radio telescopes join the watch, not in expectation of clear artificial transmissions, but to listen for changes in the way the coma and tail interact with the solar wind, and with Jupiter's powerful magnetosphere. Charged particles streaming past the object can produce faint emissions that encode information about magnetic field lines and plasma density. If the three jets act as conduits, not only for neutral gas and dust, but also for charged material,
They might leave a recognizable imprint in these radio signatures, a pattern of periodic modulation tied to the spin and jet geometry. Detecting such subtle features will be difficult, but the global nature of the campaign means many ears will be listening at once. Citizen science networks, though lacking the reach of large observatories, add another layer of coverage. Skilled amateurs with medium-sized telescopes and modern detectors can record the evolving shape of the tail night after night, filling in gaps that professional schedules cannot cover. Their images, when combined, can track the growth of any fragments if the nucleus begins to break up, or can follow the development of unusual kinks and striations that might correlate with changes in jet activity. In this way, the encounter becomes not only a test of an interstellar object, but also a rehearsal for how humans as a whole might respond to future anomalies from beyond. Throughout all this preparation, caution remains the guiding principle. No team frames its proposals or reports as a quest to confirm alien technology. Instead, the working language emphasizes understanding of cometary physics, constraints on the structure of interstellar bodies, and opportunities to refine models of tidal disruption. Yet beneath the surface of formal phrasing, the prospect that 3I Atlas might reveal some hint of deliberate navigation lives quietly in many minds. A sudden, unexplained change in course, a persistent pattern of non-gravitational acceleration aligned with the jet geometry, or a striking robustness of the threefold symmetry in the face of Jupiter's pole would not immediately prove design, but they would mark a turning point. The eyes trained on the encounter are therefore not only collecting photons and positions, they are also watching for any sign, however small, that the universe is about to answer a question that has so far received only silence. As 3I Atlas draws nearer to its encounter with Jupiter, attention turns from describing its behavior to asking what, if anything, that behavior might mean. Geometry and motion become the channels through which this object can speak. There is no carrier wave, no modulated signal, no surface markings that can be resolved at this distance. What remain are patterns, the way jets align, the way brightness rises and falls, the way the trajectory threads through the combined fields of sun and planet. If there is any intention encoded in this visitor, it will be written in these silent choices. The three jets are the clearest candidates for such a message. Their nearly equal angular spacing suggests a grasp of simple division, a preference for splitting a circle into three identical sectors. In human systems, such division appears in engineering because it minimizes wobble and distributes stress evenly. If a distant civilization faces the same physical constraints, threefold symmetry might emerge as a common solution, independent of biology or culture. The way those jets respond to changing conditions may carry further content. If they maintain their spacing through the tidal gradients near Jupiter, that persistence would speak of an underlying structure robust enough to resist distortion. If, in addition, the timing and intensity of the jets correlate with subtle shifts in the object's path, nudging it away from particular resonances or regions of higher radiation, then the combined pattern of geometry and motion would begin to resemble an algorithm, a set of rules applied to maintain preferred states. Even without conscious guidance in real time, such behavior could reflect programming embedded long ago, a mechanical instinct written into the object's design. There is also the question of energy. Natural comets squander the energy of sunlight, converting it into chaotic outgassing that erodes the nucleus without any gain beyond the release of dust and gas. An engineered system might be expected to use available energy more efficiently, directing outflow in ways that accomplish specific tasks. Three narrow jets, positioned to balance forces, look more like efficient exhausts than random leaks. If measurements of non-gravitational acceleration during and after the Jupiter encounter show that these jets produce a net force aligned with a consistent frame of reference, that would hint at deliberate use of energy rather than waste. In the absence of such clear signatures, interpretations remain open. One view treats any object that departs strongly from statistical norms, whether natural or artificial, as a kind of message from the universe about its own diversity. Under this lens, 3I Atlas serves as a demonstration that the category of interstellar wanderers is wider than previously assumed. Its symmetry becomes a data point in an emerging distribution rather than a lone signal. If future surveys reveal other objects with comparably structured jets, the current anomaly may settle into a recognized class of naturally ordered bodies. The motion of 3I Atlas through space offers further layers of possible meaning. A purely natural path would be set mainly by gravity, altered only slightly by sunlight and by the reaction forces of outgassing.
If, after accounting for these effects, the orbit still shows residual deviations that consistently preserve certain relationships, such as maintaining a particular orientation relative to Jupiter's magnetic axis, or avoiding close approaches to smaller bodies, those residuals could be read as hints of navigation. The scale of such changes might be tiny, yet even subtle steering would stand out against the background of random perturbations that typically affect comets. In thinking through these possibilities, it is important to acknowledge that meanings can be layered without being intentional. The three jets of 3I Atlas may truly be natural, yet the mathematical elegance of their arrangement still offers a kind of message about what gravity, ice, and time can accomplish in distant planetary systems. The object may be nothing more than a fragment of primordial debris, and yet in passing close to Jupiter, it will write a trace into the archives of a technological species that has only recently begun to notice such visitors. To that species, the symmetry and motion of 3I Atlas become prompts to refine instruments, expand theories, and question assumptions. Whether or not anyone built this object, it is already shaping the path of human thought. In that indirect sense, the geometry of 3I Atlas functions as a communication from the cosmos, delivered not through deliberate signaling, but through the stubborn insistence of an unlikely pattern. A pattern that says, in the simplest of forms, that the space between stars is not empty, and that within that space there exist structures whose forms are still capable of surprise. In the weeks before and after the encounter with Jupiter, 3I Atlas becomes more than a single object on a single trajectory. It turns into a focal point for a much broader story about how a young technological species listens to the cosmos. Each new frame taken by Hubble, each spectrum from a ground-based observatory, each bit of telemetry from Juno threaded through the planet's harsh radiation belts adds another thin layer to the portrait. And yet, the central questions remain unresolved. Does the visitor behave like a comet shaped by unfamiliar, but ultimately natural processes in some distant nursery? Or does its finely balanced geometry hint at a lineage of design that stretches back to minds that will never be met? For now, the answer lies suspended in patterns that are suggestive but not definitive. The three jets continue to appear in processed images, sometimes sharper, sometimes blurred by changing viewing angles and noise, but always leaning back toward that near-perfect splitting of the circle. The tail continues to billow and twist, recording in its ragged length the changing push of sunlight and the complex dance of forces around Jupiter. Early analyses of the trajectory hint at small, non-gravitational contributions, yet the uncertainties are large enough that caution prevails. Nothing in the data compels a proclamation. Nothing in the data closes the door on wonder. In the larger context of interstellar visitors, 3I Atlas takes its place beside the elongated object that once slipped through the inner system with puzzling acceleration, and the later, more conventional comet that followed a slightly straighter set of rules. Together, these few travelers begin to sketch a first, rough map of what drifts between stars. Shards of rock and ice, some ordinary, some stretched into improbable shapes, some lit by symmetrical jets that seem almost too tidy for comfort. Future surveys will surely expand this catalog. Wide-field instruments designed to scan the sky night after night will catch more hyperbolic tracks, more faint smudges that resolve under deeper scrutiny into complex comae and tails. Among them, there may be bodies whose behavior renders 3I Atlas less unique, folding its symmetry into a new class of naturally ordered objects. Or there may be visitors whose anomalies are even more striking, whose motions and structures force a reconsideration of what counts as evidence for technology. In either case, this current object serves as a bridge between an earlier era when comets were thought of mainly as dirty snowballs and a future in which interstellar debris, both natural and perhaps artificial, is recognized as a normal part of the galactic environment. On the human side of the story, the response to 3I Atlas reveals habits of thought as clearly as the data reveal the object's jets. The instinct to seek natural explanations first, to push familiar physics to its limits before invoking design, reflects a history of being surprised by nature's ingenuity. At the same time, the willingness of some researchers to entertain the possibility of a technological signature and to build careful, testable models around that possibility shows that the search for company in the universe has entered a more mature phase. Speculation is no longer confined to imaginative tales. It is being folded into serious proposals, framed in terms of measurable quantities and explicit criteria.
In this way, the debate around 3-eye atlas becomes a rehearsal for future conversations, a practice in how to weigh geometry and probability against deeply held expectations. Beyond the observatories and mission control rooms, the existence of such an object filters slowly into broader awareness. Visualizations of its orbit, artists' impressions of its 3 jets piercing the coma, and simplified explanations of its interstellar origin circulate through public channels. For many who follow these accounts, the details of rotation gradient filters and statistical confidence levels fade quickly. What remains is a simpler, quieter impression that a fragment from another star system has passed through the domain of the planets, and that within its luminous haze lies a structure that refuses to be entirely ordinary.
The universe, already vast and indifferent, gains another layer of subtlety. Out in the dark, there are objects whose very shapes pose questions. When the intense observing campaigns gradually wind down, instruments pivot back to other targets, and the data from the encounter settle into archives where future generations will revisit them with better tools. 3. I-Atlas itself recedes, either departing the solar system entirely, or, if deflected, slipping onto a path that will not return it to the inner regions for timescales far beyond any planning horizon. Its tangible presence in the sky diminishes, but the questions it raised do not. They remain embedded in models of comet formation, in roadmaps for future missions that might one day intercept interstellar wanderers at closer range, and in the quiet recognition that the next anomaly may arrive without warning. In the nights that follow, the sky returns, as it always does, to its familiar patterns. Planets trace their slow arcs, stars wheel overhead, and the band of the galaxy stretches from horizon to horizon. Somewhere along that band, in directions marked only by catalog numbers, lie the distant systems that once hosted 3-eye Atlas and its kin. Whether those systems nurtured only dust and rock, or whether they also nurtured minds capable of shaping dust and rock into purposeful forms, remains unknown. What is known is that, for a brief span of time, one of their fragments passed close enough for a small world around an ordinary star to notice, to measure, and to wonder. In that intersection of trajectories, a silent conversation takes place, carried not by words but by the angle between 3 jets, by the fine line between chance and intention, and by the readiness of a listening species to admit that its understanding of the darkness is still incomplete.